Hey students, Mr. Macnek. Today we are going to discuss gas laws. Yes, we are. Charles' law, Boyle's law, and the combined gas law. So here's where you get to apply some of your math skills to solve some problems as they relate to the relationships between temperature and pressure and volume. And we are going to look at several different examples of these gas laws. So sit back and take a few notes. We'll do a couple practice problems. You probably want your calculator by your side to help you, and we'll walk through these together, and then there will be some practice problems for you to do afterwards. So let's begin with Charles' law. So Charles' law basically states that if you have a constant pressure exerted on a gas, that the volume of gas is directly proportional to its temperature in kelvins. So yes, here's where that Kelvin scale comes into play. So we're going to have to remember there's a conversion that we have to remember when it comes to converting Celsius to Kelvin. And it's pretty simple. So we'll go through that in a minute. But to begin, we're going to take a look at the formula that we're going to use for Charles' law. So since there is a direct relationship between volume and temperature, we can basically state that the volume of a gas and its temperature, its initial temperature, is equal to the volume after either the volume or temperature was changed. So if we look at the relationship, we can basically say as the temperature of a gas increases, the volume of that gas would increase as well if the pressure on that system is held constant. So here's an example problem. So if you have a balloon that's filled with 2 liters of air and the temperature of that balloon is at 25 degrees Celsius. So if we heat the balloon up to 38 degrees Celsius, what's going to be the new volume? So we can probably conceptually think about that and realize, yeah, if we heat that volume of air, it would definitely increase. So we're going to see an increase in the volume. So now let's go through and mathematically calculate this. So the first thing is take our temperature in degrees Celsius and convert it to kelvins. So 25 degrees Celsius is equal to 25 plus 273 Kelvin. So when you do this conversion, what we know is that the freezing point of water is 273 Kelvin. So for 25 degrees Celsius, we simply add those two numbers to get our Kelvin temperature, which is 298. We do the same for our final temperature, which is 38 degrees Celsius. So now what we have to do is take these values and plug them into our formula. So we know our initial volume, we know our initial temperature, we know our final temperature. We simply have to solve for the end volume. So we know this, we know this, we know the volume 2, we want to find, or we know temperature 2, we want to figure out V2. So again, first thing when you set up any type of problem for science class, please identify what your variables are, list them out. So V1 is 2 liters, V2 is what we're trying to solve for, T1 is 298, and T2 is 311. Now we can plug the variables into our equation. So to do this, we set up our equation, and we are going to solve for V2. So to solve for V2, we can rewrite our equation so that we multiply V2 times 298, we multiply 2 liters by 311, so we can get V2 by itself. So then we divide 622 by 298, and when we end up doing this, we get a new volume of 2.09 liters. So this would be our answer. So we started with 2 liters in our balloon, and by increasing that temperature so slightly, it increased the volume to 2.09 liters. So this is an example of Charles' law, where there's a direct relationship between volume and temperature. So as temperature increases, the volume would increase. Or the opposite is true. When the temperature decreases, the volume of that gas would decrease as well. So the second law we're going to discuss today and go through a practice problem with is called Boyle's law. Boyle's law basically states if you have a gas that's at a constant temperature, when the volume of the gas changes, it's inversely proportional to the pressure. So again, Boyle's law relates volume and pressure when temperature is constant. So again, if we think about this, when you have a known pressure and a known volume when you are starting with, and either the pressure or the volume of that gas has changed, it's going to directly influence the pressure and the volume of the gas afterwards. So the relationship is indirect. As the pressure goes up, the volume goes down. Or if the pressure goes down, the volume will go up. So we can apply this mathematically to a problem like this. So if you have a balloon and it has a volume of 2 liters at 743 mmHg, this is millimeters of mercury, which is a measurement of air pressure. The pressure is increased to 2.5 atmospheres, or we can say ATM. So now we have two contrasting units for air pressure. So what's the new volume? Well, in order to do this type of problem, you have to have the same units of measure. You can't do a problem where you have two different units. So the conversion that you guys will need to know is that 1 atmosphere of pressure is equal to 760 millimeters of mercury. This is the conversion factor that will be important for you to make that conversion. You can either convert it to millimeters of mercury or atmospheres. It doesn't matter. They just need to be the same. So I'm going to convert my 743 to atmospheres. So I take 743 millimeters of mercury, I multiply it by my conversion factor of 1 over 760, which is the same as dividing it by 760, and I get a pressure of 0.98 atmospheres. Now that I have that variable defined, I can go ahead and solve my problem. So I'm trying to figure out what V2 is. So again, go through, define your variables. P1 is 0.98, P2 is 2.5 atmospheres, and the volume, the initial volume was 2. So what is my volume afterwards, after we expose the balloon to a higher pressure? So we plug our numbers into our equation. So P1 times V1 is equal to 2.5 times V2. So we can easily solve for V2 by saying that 0.98 times 2 is equal to 2.5. So now we need to take our 0.98, multiply it by 2, and divide by 2.5 to get V2. So our second volume in this problem is 0.78 liters. So again, as you can see, the pressure increased, the volume of that gas decreased. There's our indirect relationship, and we can see how much the volume actually decreased by going through this type of problem. So again, our answer is 0.78 to the previous question. So now if we take a look at both of these gas laws, Charles' law and Boyle's law. Charles' law deals with volume and temperature, and Boyle's law deals with pressure and volume. We can combine these together into what's called the combined gas law, and we can then solve for any of these variables. So if we know 2 of the 3 variables before and after, we can go ahead and solve this. So when we do something like this, if we know what the standard pressure is for a given gas, we can set this problem up correctly. So the units that I mentioned before, we can see atmospheres in some problems, we might see millimeters of mercury, or we can see kilopascals, which is another unit of measure for standard pressure. So normally if we're dealing with pressure situations here on Earth and it's not given to you, we will assume that we're dealing with 1 atmosphere. So that's standard pressure. Our standard temperature that we deal with is going to be 273 Kelvin, which is again equivalent to 0 degrees Celsius. So volume, when we do volume problems, we can see liters, milliliters, or cubic centimeters. These are all ways that we can read through problems and use those units properly. So here's an example. So if we have a gas at an initial volume of 8.33 liters and an initial pressure of 1.82 atmospheres, an initial temperature of 286 Kelvin. Simultaneously changes in its temperature, so we see a temperature increase and its volume would change accordingly, and we see that the volume actually goes down. What's the final pressure on the gas? So again, first thing we need to do is we need to go through and define our variables. So we know our initial volume is 8.33 liters. We know that our initial pressure was 1.82 atmospheres. Our initial temperature was 286 Kelvin. Our second volume was 5.72 liters. So we can see the volume is going down and the temperature on that system increased. So what's the final pressure on this gas? We want to solve for P2. So again, define all of these variables, write them down, and then we have to be able to plug them into this equation. So to do this, we simply rewrite our equation where we're solving for P2. So if we isolate P2 variable by itself, we can rewrite our equation and then we can plug in our variables to solve for P2. And if you do this, you would simply see that we would multiply our initial pressure times our initial volume times our second temperature and divide it by our starting temperature and our second volume, and we would find that the answer is 3.22 atmospheres. So this is how you would go through and solve a combined gas law problem. The biggest problem that kids face is making sure that things are labeled properly, making sure that you have uniform units when you are working with a combined gas law problem. You can't have pressure in atmospheres and millimeters of mercury. You can't have temperature in degrees Celsius and Kelvin. They have to be uniform. So always convert your temperatures to Kelvin. Always have your pressures being the same. And if you do that, you should be able to set up your equations properly and solve for the answer. So the only way that you're going to become successful at doing gas law problems is, you guessed it, practice. So if you would follow the instructions on Canvas, you will find out that there's many practice problem sets for you to accomplish. And so go through and do those and bring any questions that you have to class tomorrow.